Alright, it's Niaki. It's Niaki Osteozone. So today we are going to have the continuation of the paper November 2018 from the Zimsec exam board chemistry paper 2. So today we are starting with section B. In the previous discussion we did section A, so you need to subscribe so that you'll be notified whenever we post, right? So if you're not doing Zimsec, you need to ignore these instructions and pay attention to data. But if you're doing Zimsec, you need to stick to the instructions to the candidates, right? So we are quickly diving into section A. So always remember that we are providing tutorials in all the sciences, all the science subjects about for the A level and the O levels, and we have a lot of tutors who specialize in different specialties, right? So we are now diving into section B, right? So section B, we are starting with number 6. So we are required to answer 4 questions like I've alluded to before. So the first question says state the oxidation state of chromium in this chromium 3, right? So this one is chromium 3 obviously, right? So we are given, so let us say X, this one, and then this one minus 2, the oxidation state for oxygen. So we are having 2x right here plus minus 2 by 3 being equal to 0. So it's 2x here, and then here negative 6 being equal to 0. So 2x is equal to 6, x is equal to plus 3, right? So it's plus 3. So you can deduce that from this 3. So we said they are going to exchange the coefficients of their charges, right? And then here on this part is sodium chromate. So this one is plus 6, right? So we're going to have plus 1 here, plus 1, and then x here, and then minus 2 there, right? So we are going to say plus 1 by 2, and then here plus x, and then minus 2 by 4, right? So we're simply going to solve. So here is 2 plus x minus 8 being equal to 0. So it's x is equal to 8 minus 2, x is equal to plus 6, and we are done. So here is plus 6, right? So this one is the stable or oxidation state of chromium in alkaline solution. So we are going to understand this as we are doing A-level chemistry. This one is yellow, and then the other one is orange. This one is orange one, potassium dichromate. So this one is in acidic medium, and then this one in alkaline medium. That's why we are having sodium, right? So it's sodium hydroxide. All right, and then calculate the percentage by mass of chromium in this potassium dichromate. So it was supposed to be potassium dichromate. So potassium dichromate, we are simply going to have the mass of the chromium over mass of the compound, which is the MR by 100. So the mass of chromium, we are having 2 chromium atoms here. So from the periodic table, the mass of chromium we are having 52, right? And then by 2, since we are having 2 atoms here, so by 2 over the AR, so we are simply going to say 39, that one of potassium, 39 by 2 plus chromium by 2, right, plus oxygen 16 by 7, and then we multiply by 100, right? So we're simply going to have 104 over 294 by 100, and then this is going to give us 35.4%, and we are done. Are we together? And then we can now move on to the next part. So the next part says explain why potassium dichromate is used to test for the presence of sulfur dioxide. So potassium dichromate is used as an oxidizing agent, right? It is an oxidizing agent. Are we together? So this one is used as an oxidizing agent. So it is going to oxidize this sulfur dioxide to sulfur trioxide, right? So we are going to note the color change, right? We are going to note the color change from orange to green, right? From orange to green, orange to green, right? So we are going to note the color change. So the color change is visible. That confirms the presence of sulfur dioxide, right? So that's why we are to use potassium dichromate, right? And then we now move to number 6B. So number 6B says equal amounts of A and B were reacted together to make AB in a reversible reaction, right? So we defined a reversible reaction as a reaction which proceeds in either direction, right? It proceeds in either direction. So we are having A, and then you're having B, and then here is AB, and the reaction is endothermic, right? So we say the positive sign indicates that the reaction is endothermic. It absorbs heat, right? And then if you are to have a negative sign, the reaction was to be exothermic, meaning to say it releases heat to the surroundings, right? So complete the table to show the effect of changing the conditions on the amount of A2 and AB in the equilibrium mixture. So these are governed by the Le-Chatelier principle. You need always to understand that the Le-Chatelier principle is the one which we are to use regarding to this equilibrium reversible reaction, right? So the Le-Chatelier principle states that if a reaction or a system in equilibrium is disturbed, the equilibrium will shift to oppose the change and try to reverse it. The equilibrium will shift to oppose the change and try to reverse it, and we are done. So this is the Le-Chatelier principle. You must know this Le-Chatelier principle by heart, and always remember that whenever explaining the effects of these conditions, you must always start with the statement according to Le-Chatelier principle. According to Le-Chatelier principle, this will affect this way. This is going to do that, right? Your opening line should be according to Le-Chatelier principle. Are we together? So here we are given that we are to increase pressure, right? So here we are having gaseous phase, and then gaseous phase. So if pressure only affects those particles, reacting particles, and the products which are in gaseous phase, right? So the effect of pressure is notable in gaseous phases, right? So the question is saying we are to increase pressure. So what is the effect on A? So on A there is no change, on B there is no change. So the effect of pressure is cancelled. So the total number of moles here, we are having 2 moles, and then here we are having 2 moles, 1 more here and then 1 more there. So the total number of moles for the reactants is 2, and then for the products is 2, right? So if we are to increase pressure, we are going to favor the side with fewer number of moles of gases, right? And if we are to decrease pressure, we are going to favor the side with more gaseous molecules. Are we together? And then if we are having equal moles, the effect of pressure will cancel out. So we are going to know there is no change that we are going to observe, right? Are we together? So here, the amount of A, no change. Are we together? And then if you are to increase temperature, right? So this one is in endothermic direction, meaning to say the forward reaction is absorbing temperature, absorbing heat, in other words, right? So if you are to increase temperature, we are favoring this endothermic direction, right? If you are to increase temperature, we are favoring this endothermic direction. And then if we are to decrease temperature, we are favoring this exothermic direction to produce heat, right? So that's why we are favoring this exothermic direction. So let me clear so that you can figure it out, right? So this one is the endothermic direction, and then this one is the exothermic direction. So this one is a reversible reaction, meaning to say it proceeds in either direction, right? So the question is saying, if we are to increase temperature, we want to increase temperature in this reaction, we are going to favor this forward reaction, which is going to absorb the heat, the increased heat, so that we maintain the temperature, right? So we said according to Le-Chatelier, we are going to oppose, right? So by increasing heat, we oppose by absorbing. So the reaction which you absorb heat is the forward reaction. So we are favoring this production of AB. So the concentration of AB is going to increase. And then we are reducing these two, meaning to say the concentration of A will decrease, right? Are we together? So these are the explanations of the prediction, right? So the next part says state with a reason whether the given process is an oxidation or a reduction process. So oxidation is defined in 4 effects: the gain of oxygen, the loss of hydrogen, the loss of electrons, and then increment in oxidation number. And then a reduction is defined as the loss of oxygen, the gain of hydrogen, the gain of electrons, and then the decrement in the oxidation state or oxidation number, right? So this is the definition for reduction. And then we have redox which is defined as a reaction where we are having both reduction and oxidation, right? So a redox reaction, reduction, oxidation, right? So the first process, the discharge of oxygen during the electrolysis of water. We have two ions, we have the H plus and then the hydroxyl, the proton and the hydroxyl, right? So this one is going to be oxidized to give oxygen plus water plus electrons, right? So to balance this, we are simply going to have 4 electrons and then 4 here, and then we can have it to the end. It is balanced, right? Are we together? It is balanced ionically and stoichiometrically. So this one, it is the type of reaction. It is an oxidation reaction. Why? Because we have lost electrons, right? Loss of electrons. These are the electrons here, right? Loss of electrons. And then, so you must know these equations. And then the other one for the cathode, we are going to have the proton reduced to give hydrogen gas. So anode is defined as the electrode where oxidation takes place, and then cathode is the electrode where reduction takes place. So this one is the cathode reaction because we are having reduction, the gaining of electrons, and then this one is the anode reaction because we are having the loss of electron, oxidation, right? So you must understand this in terms of electrolysis. Are we together? And then we proceed to the other equation. So we're having magnetite. So this is magnetite. So this is the combination of ion 2 plus and ion 3. So we are going to understand this when we are doing A-level transition elements, the variability in oxidation states within the d block elements, right? So we have this conversion to ion metal. So we said we are having plus 2 and plus 3, and then we are having ion metal with the oxidation state of 0. So each element in its natural occurring state, in its elementary state, the state on the periodic table, natural occurring states, it has got an oxidation state of 0. So we are moving from plus 2 and plus 3 to 0, meaning to say we are having a decrement in the oxidation state. So it is defined as reduction. Are we together? So this is the definition, reduction. Why? Decrement in the oxidation state. As simple as that. And then we proceed to number 7. Number 7 says fig 7.1 shows a simple cell, and we are having magnesium, and we are having copper here, and then dilute sulfuric acid. So this one, these are what we call electric cells, right? So we are having the conversion of a potential energy into electrical energy, right? So you must understand the difference between these electric cells and electrolytic cells, where we are having the conversion of electric energy into potential energy, right? So you must take note of the differences, right? So we explained this in our topical series, right? Label the positive and the negative electrodes, right? So magnesium is more reactive than copper, right? From the reactivity series, meaning to say it is going to have the high concentration of electrons. It is going to lose electrons since it is going to have highest concentration of electrons, right? So this one is going to be our negative electrode. So we explained this in terms of the effects of naming the electrodes in our topical discussion. And then this one, the copper, is going to be the anode, since it has got the hunger for electrons, meaning to say it is positively charged. So it is going to attract the negative electrons, right? So this one is going to be the positive electrodes, right? So we don't define these electrodes in terms of anode and cathode using that way. So anode and cathode are only defined using this mnemonic red cat for cathode, and then anode in ox. So where we are having oxidation, that's the anode, and then where we are having reduction, that's the cathode. So this one is obviously to be our cathode, and then this one our anode, right? So we can now move on to the next part of the question. So the next part says explain how this simple cell produces the electric current, right? So for the production of current, we are having the flow of electrons from this magnesium anode, from this magnesium electrode. So electrons will flow this through this wire. Will flow through this wire to to the copper, thereby inducing electric current. So we are having the flow of electrons from magnesium to copper, right? So this is the flow, and then the flow of electrons will induce electric current. So current flows from copper to zinc. So the flow of current is from copper to magnesium, and then that one of electrons is from magnesium to copper, right? And you must also be able to define the term polarization. So polarization, it is the accumulation of the hydrogen gas bubbles on the cathode, right? So it is the accumulation of the hydrogen gas bubbles on the cathode. So we explained this in our topical series, so you need to go and you have that tutorial, right? So the next part says explain the effect, state and explain the effect of replacing magnesium with zinc. So magnesium is more reactive than zinc. So if you are to replace magnesium with zinc, we are lowering the current being produced, right? So the cell is going to produce low current, decrease voltage, right? Decrease voltage, right? So why? Because zinc is less reactive compared to magnesium. Are you together? So the difference between zinc and copper in the reactivity series is very small. So the electromotive force, the EMF, is going to be reduced, right? And then if we were to replace magnesium with copper, so magnesium here being replaced with copper, and then here we are having copper, no reaction will occur. So we are not going to produce any current, no voltage produced, right? Voltage, so it's no voltage produced. Why? Because these two, there's no reactivity difference between copper and copper, so no current, so no redox reaction. So these reactions, they occur in a series of redox processes, right? We are having reduction and then having oxidation, right? So here reduction and then here oxidation, the definition of redox. Are we together? So this is what you need to take note of. And then we now move on to B. So B says a piece of iron wire was reacted with a dilute hydrochloric acid as shown, right? So here is a piece of wire reacting with a dilute hydrochloric acid, and then we are having gas obtained using the downward displacement of water, and then here are the gas bubbles, and then the beaker, and then the water, right? So name the gas produced. So in metal with an acid, we are going to produce hydrogen gas, right? So it's iron plus hydrochloric acid to give iron 2 chloride plus hydrogen gas, right? So to balance this equation, we must have a 2 here, right? So we're going to have hydrogen gas here, right? And then the other question says describe a chemical test for the gas, right? So to test for gas, we're going to insert a burning splint, right? So we are going to insert a burning. So it's a burning for hydrogen and then glowing for oxygen. So we are going to insert a burning splint, and we are going to observe the popping sound. So hydrogen burns with a popping sound. So you must underline these terms: popping sound and a burning splint. A glowing splint, it is for oxygen, and it relights a glowing splint. Oxygen relights a glowing splint. And then to test for carbon dioxide, we are going to use lime water, which turns milky. And then for chlorine, we are going to use the litmus paper. So the blue litmus paper turns red, and then it also bleaches the litmus paper. And then for ammonia, we're going to use the red litmus paper, which turns blue, right? So these are the confirmatory tests of these gases, right? And then name with a reason the compound that remains in the conical flask, right? So name with the reason. So in the conical flask, we are going to have iron 2 chloride, right? So the compound which remains is iron 2 chloride, right? Why? Because the reaction is between diluted hydrochloric acid and iron to give iron 2 chloride, right? So this is the reason. And then suggest how the rate of the reaction at room temperature and pressure can be increased. So how best can we increase this reaction? So we can increase this reaction by increasing concentration of hydrochloric acid, by also increasing the temperature, and by using powdered iron, right? So we can use powdered iron instead of a wire, so that we can increase the surface surface area, the contact point. So we explained these effects in terms of reaction kinetics in our topic discussions, right? And also we can make use of a catalyst, right? So a catalyst, it is a chemical substance which increases the rate of a reaction by providing an alternative route with lower activation energy. Are we together? And then we move on to number 8, which says define the term isomer, right? So this is isomerism, right? So an isomer is defined as organic compounds with the same molecular formula but different structural formula or arrangement of particles in space, what you call the spatial arrangement, right? So you must know these types of formula, position, the functional group, but for O-level geometrical isomers are not that important for you. So the next question says draw a structural formula of the two branched chain isomers of a hydrocarbon, hexane, right? So this is hexane, so it's an alkane, right? So we have this general formula Cn, then H2n plus 2, right? So here we are having 12, and then 2n is 12 plus 2 to give us this 14, right? So it's an alkane, right? So we want to draw the isomers of alkane. So we are simply going to have C, and then branched here. So we can branch it here, right? And we can now count 1, 2, 3, 4, 5, and then 6. And then we are done with the first one. And then this one is the second one. So we are having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogen atoms. And we are also having 1, 2, 3, 4, 5, 6. We are having 6 carbon atoms, right? So this is 2 methyl. So the methyl group is on position number 2. So we name from the nearest locant, right? So this one is 2, right? So the longest chain 1, 2, 3, 4, 5. So it's 2 methyl pentane, and we are done, right? So this is the first one, and then for the second one we can shift this one, making it here, drawing the methyl group here, so that we can have 3 methyl pentane, and we can also have 2,2 dimethyl butane. So another one is 2,2 dimethyl butane, right? So we're simply going to have, this is the butane, and then 2, this is the position 2, right? So it's 2,2 dimethyl butane, right? And then H, and then H. So we can simply count the number of hydrogen atoms: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The number of carbon atoms: 1, 2, 3, 4, 5, 6, right? So it's 2 dimethyl butane, and we are done. Are we together? And then we can now proceed to the next part. So the next part says Fig 8.1 shows how glucose can be converted into organic compounds, right? So we are starting with glucose C6H12 and then O6, right? And then undergoing fermentation. So for fermentation, we are going to produce ethanol. So ethanol is C2H5OH, and then ethanol into ethene. This is dehydration. So dehydration or elimination reaction. So we are going to use sulfuric acid, concentrated sulfuric acid at 170 degrees Celsius, right? And then this reaction can be reversible using phosphoric acid, right, at 300 degrees Celsius, 60 to 70 atms of pressure, right? And then the produced ethene can be hydrogenated in the presence of nickel. Nickel is the catalyst, right, at a temperature of 150 degrees Celsius to give a hydro in alkane, so to give ethane here, right? So this is used in the manufacturing of margarine, right? And then we're having this one, the bromination. So this one is an addition reaction. We're adding a bromine across this double bond. So this one is an alkene, right? Meaning to say we're having a carbon to carbon double bond. So it's an alkene. We can deduce that from this formula. So formula for alkene is CnH2n. So N is 2 and then 2N is 4. So this one is obviously N alkene. So we are adding this bromine across this double bond, right? So we are having bromination. And then the polymerization, this one is addition, polymerization to form polyethene, right? So we are going to have C and then H and then H and then H and then H, and then we can have this as the polymer, right? So the question says describe the conditions necessary for fermentation. So for fermentation, we are going to have anaerobic conditions. We are going to have the absence of oxygen, right? In other words, absence of oxygen, right? And then we can also say we are going to have yeast, and then in the yeast you are going to have the enzyme zymase, which can catalyze the reaction, and then the temperature must be around 37 degrees for the optimum conditions for the enzyme zymase. Are we together? And then it must be an aqueous solution, right? Aqueous solution, and we are done. So this is awarded for 2 marks. So the important one, we are having anaerobic condition 37 and then yeast. All are important, right? And then we go on to the next one, which says name the product P. So which one is our P? So P is ethanol. We said P is ethanol, right? And then the next one says name the compound. This one. So this one is 1,2-dibromoethane. So it's 1,2, di means 2, bromo, ethane, right? So this is the compound. I think I've drawn up right. So it's and we have the bromine here, and then the hydrogen, and then hydrogen, right? So this is 1,2-dibromoethane. And then the next compound, the next question, state the type of reaction in step 2 and then step 3. Step 2, which one is our step 2? So step 2, we are having ethanol into ethene. So this one is an elimination or a dehydration reaction, right? And then type 3, this one is an addition reaction or a bromination, right? Addition or a bromination reaction. All right. So describe a chemical test for ethene. So we can use the bromination, right? So the bromination, we are adding bromine in darkness, right? So you must always highlight that we are using darkness as the condition. Why? Because in the presence of UV, in alkane can decolorize bromine water, right? So we are going to decolorize bromine from orange, the orange color of bromine water to colorless, right? And we are done. So the first mark for the reagents, and then the condition, and then the deduction, right? And then give the structural formula of the organic product Q and R. So we want Q and R. Where is our Q? So here is our R, and then our Q here. So Q is hydrogenation, right? So we're going to have the hydrogenation here, right? We are done, right? So organic chemistry is very, very easy, right? And then the next part, so it's number 9. So number 9 says Fig 9.1 shows part of the periodic table. The position of some elements is shown by the letters. So we're having M, and then W, and then R, P, Q, S, T, U, and then V. So this one is the group 1, this one group 2, this one is the D block for the transition elements, right? And then this one, the group 3, this one 4, 5, 6, 7, and lastly 8, right? Are we together, guys? So this is what you need to understand from the periodic table. This one is the period 2, period 3, 4, 5, and then 6, right? So state the letter that represents an element that forms a colored compound with chlorine. So colored compounds are formed from transition elements, right? So colored compounds are formed from transition elements. Are we together? State with the color the element, so P, right? So we are only going to have transition elements. So it is one of the properties of transition elements. They are going to form variable oxidation states, colored compounds, high density, right, and etc. So you should know these properties of the transition elements. And then draw a diagram to show the arrangement of electrons in the element represented by the letter T. Where is our T? So this one is our T. So T is in period 3, meaning to say it is having 3 shells, and in group group 7. So the electronic configuration, we want to have 3 shells and then the last shell with 7 electrons, right? 3 shells, period 3, and then the last shell is having 7 electrons, and we are done. So you must know that all these other shells are filled. For us to have 3 shells, this simply means to say the other 2 shells are filled, and then this number here represents the number of electrons in the outermost shell. Are we together? So you must understand the laws we explained before, the laws when filling orbitals, when filling shells. We can't proceed to the next shell before completely filling the previous shell. Are we together? So if you are having the element in period 3, this simply means to say all the other previous shells are full of electrons. And then we said the first shell is filled with 2, the next, all the other shells are filled with 8 electrons. Are we together? So this is what you need to understand, right? And then we now move on to the next part, which says state 2 letters that represents the elements that react together most vigorously. The elements that react together most vigorously. So we're going to have so the most element which is very, very reactive, it is R, which is in group 1 in terms of electropositivity. So R is ready to lose its electron, right? And then the most element which is a non-metal which is very reactive, having T, right? So T will then react in terms of electron negativity. It has got the highest tendency of receiving electrons, and then R highest tendency of losing electrons. So we are going to have a more vigorous reaction between these two. Are we together? So it's R and T. So it's R and T. And then we can now proceed to the next part, which says describe and explain how the atomic radii changes down the group from the element T to V. Describe and then we explain. Alright, so it's T and V. So where is our T? Where is our T? So here is our T and then here is our V. So the trend of atomic radii, so the atomic radii is going to increase as we go down the group. Why? Because we are having an extra shells being added. So we are going to have an increment of the atomic radii, right? So atomic radii will increase. Why? Because we are having an extra shell being added as we go down the group, right? So we are going to have additional electron shells as we go down the group, and it is awarded for 2 marks, right? And then the next question says explain why the element represented by W is a metal. Where is our W? So W is in group 2, so we said all group 2 elements are metals, right? So all group 2 elements are metals. Explain why it is a metal. Because it is in group 2, right? So it reacts by losing electrons, 2 electrons in the outermost shell. So we can't explain in terms of ionization energy here. Why? Because we haven't done ionization energy for O level, right? And then T is a non-metal. So where is our T? So here is our T. So T, because it is a non-metal, it reacts by losing electrons. So it is in group 7, right? So T is in group 7. It reacts by gaining electrons. Right? And we are done. And then the next part says state with a reason the acid-base nature of the oxide of the element represented by Q. Alright, where is our Q? So Q is aluminium, right? It resembles aluminium. So in other words, it is an amphoteric. It is an amphoteric nature. The ability to react with both acids and bases. So aluminium oxide is amphoteric in nature. It reacts with both acids and bases, right? So you must understand that. So we move to the next question. So the next question says describe and explain the trend of volatility of group 7 elements. So volatility is defined as the ease of a substance to vaporize, to turn from a liquid to a gas. So this is governed by the lattice structure. strength of the forces holding the particles together, right? So we are going to explain using the periodic table. Molecules, we have what you call the van der Waals forces. So this is for you guys to just to understand, right? We have the forces which you call the van der Waals forces. So for all level, just know the mass forces, right? We have the forces. So the strength of these forces, they increase with increase in number of electrons and molecular size. So as we go down the group, the molecules are going to be bigger since we are adding in extra shell, right? So we are also increasing the number of electrons, right? Are we together, guys? So we are having an increment in the molecular size, an increment in the number of electrons, meaning to say the strength of the forces is going to increase. So that's why we are starting with fluorine, which is a gas, chlorine, a gas, and then we are going to have bromine, which is a liquid, and then we are going to have iodine, which is a solid. Right? So we are having an increment in the strength of the forces as we go down the group, meaning to say the ability to change from liquid to gas is going to decrease as we go down the group. Why? Because the forces are going to be stronger as we go down the group. So the strength of the forces increases as we go down the group. Are we together? So you must understand, you must know this by heart. So we are now moving on to number 10. Number 10 says Fig 10.1 shows some of the reactions of soluble transition metal compound Y, right? So this is Y, and then to Y we are adding sodium hydroxide, and then we are going to observe the green precipitate, which is insoluble in excess, meaning to say we are having iron 2 plus, right? So this is transition elements quantitative analysis. So this is qualitative analysis, right? So if you are to expose this iron 2 in A, we're going to have the oxidation to iron 3, right? So we're going to have the color changing to brown, right? Since we are oxidizing to iron 3. But is this for all level? So this was abuse, because this is not for all level, right? So we now move to the anion, right? So for the anions, we're adding a silver nitrate plus D. So D is nitric acid. So it's supposed to be in acidic medium, right? And then we're going to observe the white precipitate. So the white precipitate indicates the chloride ions. And then we are going to add ammonia solution. So we're going to form a silver diamine. So this is not for all level. This is not for all level, right? Then this is transition elements, right? So we are going to form silver diamine. So this one is going to dissolve in ammonia to form silver diamine, right? Which is E. So we can now conclude, we can now deduce that our Y is iron 2 chloride. But I don't think this one is for you guys. And then deduce the molecular formula of Y is iron 2 chloride. And then describe the color of Y. So the color of Y, it is a pale green solution, right? We are having white and green, so we're going to have a pale green solution, right? And then identify the substance B, C, and then D. B, which one is our B? Here is our B, so it's iron 3. And then iron 3 hydroxide, so here it's iron 3 hydroxide, right? And then our D, we are going to have nitric acid, and then our E, we are going to have silver diamine. But this is not for you guys, right? And then we can now to the next part. So the next part says describe the observations made during the formation of E. So which one is our E? So the white precipitate will dissolve in ammonia to form silver diamine, right? And then name the chemical method used to obtain iron in the blast furnace, right? So we are going to have the reduction method using carbon, right? So it is called the carbon reduction procedure. And then explain why silicon dioxide is used to construct bricks of the blast furnace walls, right? So silicon dioxide exhibits, so this is a giant molecular, so it exhibits a giant molecular lattice structure. So the forces, the covalent bonds extends throughout the structure, which are strong to withstand temperatures in the blast furnace. That's why it is used, right? And then magnesium oxide is used as a refractory lining in the blast furnaces. So refractory materials are those which are able to withstand high temperatures. So it is used because it is a giant ionic, it exhibits a giant ionic lattice structure where the particles are held by the strong electrostatic force of attraction between the positive magnesium cation and the negative oxide anion. So the forces are able to withstand the high temperatures. Are you together? And then we go on to the next part, which is the blast furnace is never extinguished. This is done so because in the blast furnace we are having high temperatures of about 1500 degrees Celsius. So if we are to extinguish it, the process of restarting it is going to be expensive, right? So we want to avoid the cost of restarting it. And also we are having molten iron and slag, so this can solidify if you are to extinguish it, and to remove it is gonna be difficult for us, right? And then I'll give the chemical formula for slag. Slag is formed between calcium oxide plus silicon dioxide. So we are simply going to have calcium silicate, and we are done. So the next question says state the role of slag in the blast furnace. So here we say the slag, we are going to form slag. So the other role of slag, though it is not a direct impurity, right? It is formed from impurities, right? So the other role is to remove impurities. Slag is formed from impurities, but itself it is not an impurity, so it is used to remove the impurities, right? Remove impurities, right? And then the next question says give two advantages of the use of alloy over pure metals. So alloy, they have the desired characteristics, meaning to say they are harder and are stronger compared to pure metals, and also they can resist corrosion, right? So corrosion resistance, right? And we can now move to the next part, and we are done.